Hello dear students, welcome back to the lecture series based on theory of semigroups. We continue this lecture. In the previous lecture, the topic was monogenic semigroups. So in this lecture, we'll prove the following theorem. As in case of groups, the cyclogroups, there is a theorem which is called a structure theorem for cyclogroups. Which states that a cyclogroup is either isomorphic to the group of integers under addition, or it is isomorphic to Z mod n. And we have the same theorem here for monogenic semigroups. So let us state this theorem. Let A be an element of element of a semigroup S, element of a semigroup S. Then either all the powers of A are distinct, either all the powers of A are distinct, they are all distinct, and in that case, if all the powers of A are distinct, then this monogenic subsemigroup and monogenic subsemigroup generated by A of S is isomorphic to the semigroup of natural numbers with plus operation additive. What for this? Or so in this so in the first case, if all the powers of A are distinct, then in that case this monogenic subsemigroup it's infinite and it will be isomorphic to n plus. And second case, if there is a repetition, so this part is very important. If there exists a positive integer, second case, there exists positive integers m, which we call the index of A, and the second integer which we denote by R, and it's called the period of A. Okay. So in case all the powers of A are distinct, then it is isomorphic to n plus, and in second case, if there is repetition, then we will see that there exist positive integers m, the index of A, or the period of A, with the following properties. First property is M and R. They satisfy the following property: A for M is equal to A for M plus R. And second property is for all U comma V in n, 0 means the natural numbers together with 0. So it's a set of whole numbers, 0, 1, 2, so on. So u comma v belongs to n0, with then this a power m plus u is equal to a power m plus v if and only if u is congruent to v mod r. That's the second property. And the third property is it's property C. Sorry. Third property, the monogenic semigroup generated by A is equal to, in this case, it's equal to a square a power m, then a power m plus 1, a power m plus r minus 1. So in this case, if there is repetition, then this monogenic semigroup is equal to this list of elements, list of powers of A. So their total numbers is m plus r minus 1. It's finite in this case. And the fourth property is the set Ka, we denote it by K, and it's equal to a power m plus 1, a power m plus r minus 1. This set is a cyclic subgroup of monogenic subsemigroup A, is a cyclic subgroup of monogenic subsemigroup A. Is a cyclic subgroup of A. Okay. Monogenic subsemigroup A. So that's the statement of this theorem. So that A be an element of a semigroup S, then either all the powers of A are distinct, and in this case the semigroup generated by A, the monogenic subsemigroup A of S, is isomorphic to the semigroup of natural numbers under addition operation. And in the second case, if there is repetition, then there exists positive integers m, which we call the index of A, or the period of A, with the following properties: a power m is equal to a power m plus r, and for all u belongs to n0, the set of natural numbers together along with 0, including this 0 as also in this set, n0. Okay, so u and v may be 0. Then this a power m plus u is equal to a power m plus v if and only if u is congruent to v mod r. And third property of the second case is this monogenic subsemigroup is equal to that set. And fourth, the subset of this a power m plus 1, a power m plus r minus 1, this is a cyclic subgroup of this. So let's prove this theorem. Then we give some examples, then we explain, then we illustrate this theorem with the help of some examples. Proof. Now suppose there is no repetition. So let A belongs to S. First part. Suppose powers of A are distinct. So then we can say two powers are equal if and only if m is equal to n, because powers are distinct. So if m is not equal to n, then a power m cannot be equal to a power n, because all the powers are distinct. So that means they are equal if and only if their powers are same. If only these m and n are same. So this is the case if the powers of A are distinct. So this can be written as a power m is equal to a power n if and only if m is equal to n. Now we define. Now we show that we show that the monogenic subsemigroup, which is equal to, in this case, is equal to a square infinite set, because all the powers are distinct, is isomorphic to the semigroup of natural numbers under addition. So for this we need to define a map. So define psi from n, set of natural numbers, to this monogenic semigroup by psi of n is equal to a power n. That's a natural way to define this map. We will show that this map is bijective, and it is also semigroup morphism. It's a morphism. We show that psi is an isomorphism. So let us first prove psi is bijective. Psi is bijective. So it's a map from n to a. So let psi is bijective. So let n comma m belongs to n such that psi of n is equal to psi of m. We show that n is equal to n, that means one oneness. So we prove first one oneness property of psi, which implies a power n is equal to a power m. Since all the powers are distinct, so if they are equal, then this means n is equal to m. So that proves therefore psi is 1 1. Therefore psi is 1 1. Next we prove it's also onto. For onto we need choose any element from this the finite monogenic semigroup A. We have to choose an element from this set, from this semigroup, and we need to show that this every element of this finite this monogenic semigroup has an pre-image in semigroup of natural numbers. So let's choose any element. Let x belongs to this. Since all the elements of that semigroup they are all the powers of a, so which implies their x some n belongs to n such that x is equal to a power n, but by definition a power n is equal to psi of n. So therefore for all x in this monogenic semigroup there exists n in n such that psi of n is equal to x. So which proves therefore psi is onto. So hence this psi is bijective. So next we show that it is a morphism. It's morphism. Now second one. Psi is morphism. So let's take any two elements in the domain, which is n, then psi of n plus m, because n here the operation is addition here, n plus m is equal to a power n plus m, which is equal to a power n into a power m, that's equal to psi of n into psi of m. So therefore psi is morphism. So hence in this case this is isomorphic to n with plus operation. So there is no repetition. Now we discuss its second case. Suppose there is repetition. Second one. Suppose now there are repetition. They are not all distinct. Suppose that the powers of A are not distinctive. They are not distinct. That is, there are repetitions among them. That is, there are repetitions among the powers of A. Suppose there are repetitions among the powers of A. Okay, among the powers of A. Then the set this x belongs to n, a natural number, such that there exists y in n with the property that a power x is equal to a power y, where x is not equal to y. So then this set must be non-empty, because in case it is empty, then there is no any x and y such that a power x equal to a power y with x not equal to y. So in that case, powers of A are all distinct. Since here the powers are not distinct, so therefore there must exist some x, there is some natural number x such that there exists y in n with a power x equal to a power y. Because if this set is empty, then there is no repetition, and that case already discussed. So this is the case when the powers of there is a repetition among the powers of A. Okay. Then the above set, is non-empty subset of set of natural numbers. Non-empty subset of set of natural numbers. So if it's non-empty set of set of natural numbers, subset of set of natural numbers, then this set must have a least element or a minimal element. So hence has the least element, it has the least element. So let R be its least element. Not R, it's M. Let's denote this by M. Let M be its least element. So that is where this M belongs to the set X belongs to N, so that there exists Y in N with a power X equal to a power M, but X is not equal to Y. So M is the least element of this set. M belongs to this set. So so now we take the following. Now we consider the following set. Now we take another set. So we have here M, a power M is equal to a power Y. So Y is greater than X actually here, because we are increasing the powers. First we take a square, a cube. So at the mth stage, a power M, then we have a power M plus 1, then we have a power M plus 2. Then at some stage, this a power M plus some element is equal to a power that M. So there is a repetition actually here at the mth stage, a power M, then we have a power M plus 1, then we have a power M plus 2. So some power of A, say a power M plus something, will be equal to a power M because of the repetition. So M is the least with this property. So that means so therefore there exists Y in N such that a power M is equal to a power Y, where this M is not equal to X. So obviously this M is not equal to Y, sorry, this M is greater than Y. This is trivial. M is greater than Y. So there is some Y. So that means that is the set X belongs to N such that a power M is equal to a power M plus X is non-empty. Is non-empty. because there is some element, there is some rational number which is greater than m, say m plus x, such that a power m is equal to a power m plus x here. There is y, such that a power m is equal to a power y, where this y is greater than m. It's m plus some integer. So there exists n. And let r be its least element. Suppose r is the least element of this set, r be its least element. Then a power m is equal to a power m plus r. So m and r, they are the least positive integers such that a power m is equal to a power m plus r. So that is m and r are the least positive integers, are the least positive integers such that a power m is equal to a power m plus r. They are the least positive integers. And this least positive integer m, it's called the index of a. It's called the index of a. And r is called the period of a. Okay, this r is called the period of a, m is called the index of a. The least positive integers, the least positive integers m and r are called the index and period of a respectively. They are called the index and period of a respectively. Or they are also called the index and period of, you can say it's also, they are index and periods of this monogenic semigroup A, or A, that's one and the same thing actually. Index and period of A. So now we have this. Now a power m, which is equal to a power m plus r, and this is equal to a power m into a power r. A power m is again equal to a power m plus r, a power m plus r into a power r. So that's equal to a power m plus 2r. And similarly, you can see it's equal to a power m plus 3r, and so on. So thus we have, if we continue this process, thus we have a power m is equal to a power m plus qr for every positive integer q, for every q greater or equal to 1. This can be proved with the